Hi, we are going to look at the homework problems from lesson 221A. Problem 12. Junior is saving money in his piggy bank. He starts with 10 cents and adds 2 pennies each day. Create an XY table and a graph for the function for which X represents the number of days since Junior started saving money and Y represents the total money he saved. So let's start by making a table. So I'm going to make a T chart. So XY. And so when you make T-charts, anytime the X value is 0 in a story problem, 0 that means the starting amount. So this is when time starts, okay? For that initial amount. So he started with 10 cents. So when X is 0, Y is 10. So then we're going to say after 1 day, he has 2 cents. So that's going to give me 12. After 2 days, 14. 3 days, 16. 4 days, 18. And 5 days, he's up to 20. And dot, dot, dot. So now, here's what we're going to do. So now we're going to plot these points on the graph. So let's find 0, 10's right here. So we're going to plot a point there. Okay. Now, the thing we have to remember is that he doesn't get coins every single minute every day. So what happens is throughout the first day, he's still at 1. So we're going to draw a line that goes from here to here. Then we have an empty circle here because this empty circle means throughout the whole day he has 10 cents. And then day 1, he goes up to 12. And then he's going to go the whole day. Then 0. Then he goes up next day to 14. Whoops. And up here. So this keeps happening every day. He goes up 2 units, 2 cents every day. So whenever you graph something, your graph should go through the entire time. So I graph until I can't graph anymore. That's kind of what we should be doing. Notice he always has a whole dot on the starting day. So, the day X value. Then at the end of the bar, he has an empty dot. Empty dots mean that isn't actually a point there. It's more of a reference. So this is the number of days. Down here, so we always label our axes. And this is money he has. And money is measured in cents. So now what we call these graphs when they have like this staircase, this is called a step graph. So there'll be many cases where we will be graphing step graphs throughout this course. So there is that problem. Okay, problem 113 says use the zero product property in factoring when necessary to solve for x. The math notes box in lesson 114 may be useful if you need help. So at this point, go in your ebook, look at lesson 144 and find the math box there, and that might be helpful. But we're going to try to show you how to do this without using that box. So the zero product property says this. So we'll type this up here, zero product property. So essentially says if A times B equals 0, then for that to be true, then either A equals 0 or B equals 0. So you see in problems A and B how we have two things being multiplied and the product is 0. So the zero product property says as long as one of those things is equal to 0, the whole product will be 0. So how you use that, these two equations are in their factored form because you got a polynomial times another polynomial. That's called factored form. So all we're going to do is we're going to take the first factor, x minus 13, we set that equal to 0. Whatever makes that equal 0 will be one of the values of x that makes this whole thing 0. So we're going to subtract 13. So when x is negative 13, this whole equation will equal 0 because 0 times something equals 0. Or, according to property, I let x minus 7 equal 0. So add the 7. So the solutions would be when x is negative 13 or positive 7, that will make this equation 0 because 13 makes the first factor equal 0. 0 times anything is 0. And positive 7 makes the second factor equal 0. Something times 0 is 0. So anytime I want to solve an equation when they're in factor form, that's what I do. So part B, again, it's in factored form. So I'm going to take the first factor, set it equals 0. So subtract 3, and then divide by 2. So one of the answers is negative 3 halves. Or I can let 3x minus 7 equal 0. So again, solve it for x. I'm going to add 7 to both sides, then divide by 3. And so since 7/3 is a repeating decimal, we want to leave our answers in improper fraction form. So my answers are x can be either negative 3 halves or 7/3. Hopefully that's making sense to you. Okay, next slide, C and D. So we got x times x minus 3. So x, okay, that is its own factor. So we're going to let x equal 0. And that means when 0 is what x equals, this is going to be 0. So 0 is an answer, or x minus 3 can equal 0. So add 3, I get 3. So for this, the answers are 0 or 3. Okay, so for part D, we have a equation that is not factored, so I need to factor it. So to factor equations, the first thing we do is we look at each term in the equation. We ask ourselves, is there something they all have in common that they're all divisible by? Well, we see that each one has an x in it. They each have one x. So I can bring that out front. That's called the greatest common factor. Then in parentheses, I write what's left over. So x times what gives you x squared? Well, that's x. So I'll move the x in there. X times what gives you negative 5? Well, that's 5x. Well, that's negative 5. So that's going to equal 0. And by bringing out the GCF, now I have something in factored form. So now I can use the zero product property like I did in parts A through C to solve this. So I let x equal 0. So one answer is 0. Or I let x minus 5 equal 0. So I add 5. So I get that for this problem, x is either 0 or 5. Those are my answers to that problem. Okay, E and F. So these are not in factor form again, but notice how in E and F there is no common factor. So we have to have another process. I'm going to show you this on the side. I like to use an area model to do this. So we're going to make a 2 by, whenever I factor quadratic trinomials, a expression with the highest exponent of 2 in 3 terms, I make a 2 by 2 box. And this may look familiar from Algebra 1, but it's worth refreshing. So I take the x squared term and put it in the top left-hand corner, and take whatever this number is, we're going to call that the c value, put that in the bottom right-hand corner. Now, the two things in the box, okay, and you maybe remember the diamond game here. So make a diamond. We did this in Algebra 1. Okay, the diamond looks like this. So up top, we put what we want the sum to be. So the sum is always going to be equal to the middle thing. In this case, I want a negative 2x, and I want a product equal to the first and last thing. So that'd be negative 35x squared. So because I want an x squared product, I need two x's. Then I'm going to look at the numbers. So this is my sum, this is my product. So I need two numbers that add to give me negative 2 and multiply to give me negative 35. Well, that would be negative 7 and positive 5. So what I put in the other boxes is a negative 7x and a positive 5x. One thing I want to show you is that when you take these diagonals, so this diagonal I'm circling in red, with these factoring problems, that diagonal red and the diagonal in orange, they should always be the same product if you do this correct. Okay, so now we are ready to factor. So what you do is you're going to bring out the greatest common factor of this first column. So x squared and 5x have one x in common. So put it on top, and then I fill out the rest of the sides by figuring out what I multiply by x at the other two terms. So x times what gives you x squared? Well, that's x. So I'm going to put x here. X times what gives you 5x? Well, that's a positive 5. Now, if this is x, if this right here is really x, x times what gives you negative 7x? Well, that would be a negative 7. And so when you take the terms on the edges of the box and you multiply them, that should give you the original expression. So that's how I factor it. And now I set those equal to 0. So I say, well, x minus 7 has to equal 0, or x plus 5 has to equal 0. So add 7, I get x equals 7. Subtract 5, I get x equals negative 5. And so my answers are x is negative 5 or positive 7. Okay, last one, 3x squared plus 14x minus 5. So again, no GCF, so I'm going to make my box. Okay. Let's put the x squared term up top, so 3x squared. The c term at bottom. So remember how I got these numbers. So I want them to add to be the term in the middle. So I want a sum of 14x and a product of first times last. So 3x squared times negative 5 is negative 15x squared. So I like to write them on the side. So what two numbers add to give me positive 14 and multiply give me negative 15? That would be 15x and negative x. And you can see the diagonals are the same. The GCF of this first column is x. X times 3x gives me 3x squared. X times negative 1 gives me negative x. So what do you multiply 3x by to get 15x? Well, that's a positive 5. And so this factors into x plus 5 and 3x minus 1. And so that should still equal 0. So now so that's a crappy 0. So either x plus 5 is going to equal 0, or 3x minus 1 is going to equal 0. So subtract 5, get negative 5. Over here, I'm going to add 1 and divide by 3. So my answers are x is going to be either 1/3 or negative 5. Okay, next one. 114. Terry's math project for the math fair was a magnificent black box that she called a function machine. If you put a 3 into her machine, the output would be 8. If you put in 10, the output would be 29. If you put in 20, the output would be 59. So this is what would her machine do to the input of 5, and how about negative 1? What about x? So we're going to make a table first to see if there's a pattern. So we're going to make a table. We're going to order the outputs in order. So sorry, the inputs in order. So the first input was a 3. It gives me an 8. The next one is a 10. That gives me a 29. And the next one is 20. And that would give me 59. So my question is, what do I do to these x's to get these y's? Well, my first thought is if I take this number, so if I take 3, and then multiply that by 3, and then subtract that by 1, I believe that should give me 8. So 3 times 3 is 9, minus 1 is 8. So if I triple the input and then subtract 1, it should work out. So let's try 10. So 10 times 3, that's 30, minus 1 is 29. That works out. So 20 times 3 is 60, minus 1 is 59. So it looks like if I triple x, then I subtract 1, that should give me my new output. So let's try. So it says 5. So for 5, what do you get? So let's triple 5. 5 tripled is 15. So 15 minus 1 is 14. So I should expect to get 14 there. How about negative 1? Triple negative 1, I get negative 3. Minus that gives me negative 4. And how about x? Well, if I triple x, whoops, if I triple x, I get 3x. And so 3x minus 1 is simply 3x minus 1. So there are my results for that. Now, part B, write an equation for a machine. Well, if we look back at problem A, we saw that when I put in x, I get 3x minus 1. That's the output. So my equation is going to be y equals the output I get with x, which was triple x, and then subtract 1. And so I should get y equals 3x minus 1, and that should go in here in Terry's machine. So I will replace that with that in the machine. Okay, for 115, Nafisa graphed a line with a slope 5 and a y-intercept of negative 2. So first, write an equation for her line. Well, I have a slope and an intercept, so that means I should use the slope-intercept form. So recall from the math notes in this lesson that slope-intercept form is y equals mx plus b. So the slope is m, the y-intercept is b. So my equation, the slope is 5. So I'm going to replace the m with a 5. So it's 5 times x. And the y-intercept is 0, negative 2. So I care about the y-coordinate of that point. That is b. So instead of plus b, it's going to be minus 2. So that's the equation for that line. Part B says find the value of x and y is 0. So what you're going to do is take the equation I wrote and replace the y with a 0. So I get that. Now solve that for x. So to solve that for x, we're going to add the 2 over. So I get 2 equals 5x. And we divide by 2. So x is going to equal 5 over 2. So there is the answer to that problem. Okay, 116. In each of the following equations, what is y when x is 2? What is y when x is 0? Where would the graph of each line cross the y-axis? So let's figure out for A when x is 2. So all that means is you're going to take and you're going to replace in the equation where x is with the 2. So it's like that. So it's 3 times 2 is 6 plus 15 is 21. So when x is 2y is 21 there. When x is 0, it's doing the same thing. 3 times 0 instead of 2 now. Well, 3 times 0 is 0. 0 plus 15 is 15. Now, where would it graph cross the y-axis? So if you look at a graph, here's the y-axis, and any point on the y-axis, right? This is the y-axis. Any point on the y-axis has an x value of 0. So it turns out when you solve when you plug in 0 into an equation, you're actually finding the y-intercept. So since we got 15 out here, where across the y-axis or the y-intercept for this function would be 0, 15. I could have also recognized, hey, this is in slope-intercept form, so B's are y-intercepts. So let's repeat this for the part B. So again, when x is 2, I get y equals 3 minus 3 times 2. Well, 3 times 2 is 6, and 3 minus 6 is negative 3. So when x is 0, I get y equals 3 minus 3 times 0. 3 times 0 is 0. 3 minus 0 is 3. And so again, where it crosses the y-axis or the y-intercept is what I get when x is 0. I got 3, so I would get 0, 3 as the point where it crosses the x-axis. Okay, 117. Carmyle made a function machine. The inner workings of the machine are visible in the diagram. What will the output be in each of the following cases? So if 3 is dropped in, so we're going to put a 3 here. That means everywhere I see an x, we're going to put a 3. So I'm going to go 3 squared plus 2 times 3 plus 1. And I can evaluate that either mentally or on a calculator. I'm doing a calculator, so I get 3 squared plus 2 times 3 plus 1. When we put in a calculator, put in exactly like you wrote it with the parentheses, and I get 16. So 3 is dropped in, a 16 should drop out. So how about 4? Negative 4. So again, put negative 4 in. So anywhere I see an x, put negative 4. That's really important when you plug in negative numbers into expressions, you put those in parentheses. We get negative 4 squared plus 2 times negative 4 plus 1. It's really important because the calculator interprets negative 4 differently when you have a parenthesis versus when you don't. And so I get 9 as my answer. And so a 9 would come out here. Okay, and so the last one is negative 22.872. So that's my input, so I'm going to do that. Negative 22.872 squared plus 2 times negative 22.872 plus 1. Plug that in to my calculator. So I get, now it's kind of a big number, but it's exact, so I write out all the digits. 478.384384. Okay, last problem. 118. Does the temperature outside depend on the time of day, or does the time of day depend on the temperature outside? This may seem like a silly question, but to sketch a graph that represents this relationship, you first need to decide which axis will represent which quantity. So part A, when you graph an equation such as y equals 3x minus 5, which variable x or y depends on the other, which is not dependent, that is, which is independent. So whenever I evaluate equations, remember the value of x, I can put anything I want into it. So what value I pick is not determined by another thing. But y, however, the outcome of y is determined or dependent upon what I plug in for x. So we call the x variable is the independent variable because its value can be whatever I want. And the y values, we call that the dependent variable because the value I get in y is totally dependent upon what x is. So, which variable is independent in our situation? The temperature or the time of day? So the dependent variable, well, we know that the time of day is how I determine whether it's cooler or warmer outside. So the temperature is the dependent variable, while the independent variable is the time of day. It turns out time of day or time in general is always going to be in the independent variable. So we're going to sketch a graph. So that's important because when I sketch these graphs, we have a vertical axis and a horizontal one. That's really bad. Let's try it again. Vertical, horizontal. Now, remember, vertical is y. Y is dependent, so this is going to be my temperature. And x is x, that the horizontal, sorry, is x, that's dependent. This is time of day. So that should be 0. So we know the temperature usually starts like this. It gets warmer. It's warmer, 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 warmer. Then middle of the day, then it starts to cool off. So temperature will look something like that as a rough sketch. Okay, hopefully this was helpful. We will see you in the next lesson's solution PowerPoint.